Okay, so we're starting in chapter 13 here. We're going to talk briefly today about some things like thermal expansion. Thermal expansion can be done just by length. Of course, it could also extend length and width, which would be a change in area. It could also do it in 3 dimensions, which of course obviously it does. And so you'd have a change in volume. So you'd have linear expansion, you'd have area expansion, you have volumetric expansion. Okay, so those are all 3 different ways we can do this thing. Now, the way it works is this. Of course, everything we do is going to be in Celsius. Okay, so it's going to work like this. The change in the length of something is going to be equal to alpha, which is the thermal expansion coefficient of linear expansion, times the original length times the change in temperature. Now, if you think about this, this is in meters, obviously. This is in, I don't know yet, this is in meters. This is in degrees Celsius. So this is obviously per degree Celsius. Okay? Because those have to cancel out. And so when we look at it, you think, oh, okay, well, like, what can it be? Well, for instance, let's say you got a piece of steel. And it was 3 meters long initially. All right, cool. Oops. And then, and it changed from being 40 degrees, 40 to 250 degrees C. So that's 210 difference. Positive 210, so it's going to expand because contraction is the same thing. And then it's 1.2 times 10 to the minus 5 is your alpha. Now, if you're looking at the book on page 353, you will notice that only the top one seems to have the 10 to the minus 5. But it's actually all of them that have it. So just be aware of that. So if your thing was 3 meters long, your piece of steel. Oh, poop. It's going to grow about 7.5 millimeters. Okay. Noticeable? Yeah. 100%. In fact, in the shop, we'll oftentimes heat something up to get it to slide on nicer. So a few years ago, took this piece of steel ring. It's a ring gear, we call it. So it's a piece of metal, thin ring of metal with teeth on it, right? This all in here is hollow. And it has to fit over this solid piece is solid. This has to fit on the outside of that. Okay. So you heat this baby up with a torch and then sit it on top there and it drops right on because it expands. You know, and 7 millimeters is, well, it's not nothing. It's quite a bit actually. Well, it wouldn't have been quite that much for that particular one. Now, if you want to do area or volume in either case, now there's some things that obviously only expand in volume. Like water only expands in volume. But let's say you took this piece of steel, okay, and you heated it, and the whole thing went from, I don't know, 40 to 160 degrees C, okay, well, then the whole thing is going to grow in every dimension. And so what you're going to end up with is that the change in volume for this piece of steel again, or brass, or whatever you want to do, is actually going to be 3 times alpha, because that's how you would get it for something like a piece of steel, brass, aluminum, whatever, something that can grow lengthwise. You can be concerned with the area or the volume. This is how you would find the coefficient of volumetric expansion. But again, for water, for alcohol, and things of that nature, why it wouldn't be, there would just be an amount for the volume expansion for water, alcohol, what have you. So in our case, let's say it's a piece of steel. And let's say that initially, so it's 3 times 1.2 e minus 5. And then let's say the initial volume was 0.5 meters, 0.5 meters, 0.7 meters. So 0.175 cubic meters. And then just so you're aware, 0.7175 cubic meters seems like it's pretty small, but it's actually a decent sized amount. And so when you do this, and you get 0.0075 6 cubic meters is the change, which doesn't seem like a lot, but it actually is a fairly healthy amount, you know, if you think about it. Yeah. So that's pretty straightforward. If it's water, let's say, or let's do alcohol. What's the alcohol one? Alcohol. Of course it is. Is 7.5 E minus 4. And for the things where, again, like a liquid, you can only change this. It's going to be given as beta. That's the coefficient of volumetric expansion. And so delta volume is equal to beta volume times time. And so let's say you had, 2 liters of water, or 2 liters of alcohol rather. And you heat it from 0 degrees C to 0 degrees to 60 degrees C, so change is 60. You get 0.09 liters, which is, you know, a healthy amount. Okay. Gotta figure that out. Come on. Come on, darling. Hello, wall. Three ounces. So, I mean, it's not like it's not nothing, right? It's not nothing. What's that, a quarter of a cup, I guess? That's pretty good. So, you know, it's not terrible. Anyway, whatever. So, suffice to say, there we have it. Now, a couple places this shows up in our daily lives. Again, making things fit onto things. In the shop, we'll have a shaft like so. And you got to slide a bearing. That's just a big plate on the bottom. You have this bearing here. And this hole in this bearing, let's say the shaft is a 1/2 inch shaft. And this hole here is 0.501. And I'm going to tell you right now, it will not slide on there. You're like, well, it's 1/1000 bigger. Yeah, it's not going to slide on there. What I would like it to be is I'd like it to be to where it would just flop down on there. So, for instance, let's say we needed to get it to 0.504. How hot would I have to get it? Well, what's going to happen here is this. That's the diameter of the hole. Are you with me? What's going to happen is that diameter of the hole is that piece of metal gets hot, it's going to expand, and the hole is also going to expand. And so if you think about that, so it's going to be a delta distance is what I'm looking for, a delta length. And so if it's made out of, I don't know, let's just do steel because I got that one off the top of my head right now, but whatever. Times 0.501 and then delta T, but I want my delta length to be 0.03. 0.003 rather. Well, then how hot would it need to be? Well, let's find out. Let's ask Betsy. Oh, Betsy. 0.003. divide by parentheses 1.2 E, oh crap, E minus 5 times 0.501. You need to heat it to about 4. You need to have a delta T of 499 degrees C. 499 degrees C. Delta. So if right now it's 20 degrees C, you're going to have to heat it up to 519 to get it to go on. Okay, but that's our delta. We solve for our delta. Okay, that's easy. Now, some people will do it this way, like, oh, it's temperature final minus temperature naught. And if my temperature naught was like 20, then you can say, that's stupid. Just find the delta first, and then if you know what the temperature is now, you got to get that much hotter, 499 degrees hotter than it currently is. Nice. And then it'll slip right on there. Okay. Piece of cake, baby. Piece of cake. Next thing I want to chat about is what's called the ideal gas law. And everybody has seen this. That is, the pressure times volume over temperature is a constant. Now, the cool thing about PV over T as a constant means that if I tell you the initial, and then if I told you, hey, two of these two guys, could you find the third one? The answer is obviously you could. Okay. A couple things to think about here. Temperature needs to be in Kelvin. If it's been a while, Kelvin is equal to Celsius plus 273. So absolute zero is negative 273 degrees Celsius, for instance. Okay. And so 0 degrees Celsius, 273 degrees Kelvin. That is why this is important, is because if this is absolute zero, if we can actually get there, right? If it's absolute zero, then everything out from there is proportional. Because this is a proportionality constant, then T has to be able to go down all the way to zero. Okay? It's a proportional thing. Now, a couple things to think about. What is pressure? What are volume measured in? It doesn't really matter. It doesn't really matter at all. Okay? So as long as you use the same units on both sides. So, for instance, for pressure, some common units we could use are PSI, pounds per square inch, pascals, bars, kilopascals, etc., etc. Those are all pretty common units for pressure. Volume, of course, you could always use cubic meters, liters, cubic centimeters, or maybe cc's, you'd write it that way. You could use cubic feet too. It wouldn't make any difference as long as it's the same on both sides. Couple things to note. If you hold T constant, then you get PV equals PV. This is known as Boyle's law. Okay? If you hold pressure constant, you get Charles' law. If you hold pressure constant, then you get VT over VT, and we call this Charles' law. Now, in the old days, I used to teach that a lot, and I would be like, oh, yeah. No, listen, it's the ideal gas law. That's it right there. Okay? And it makes perfect sense if you just look at it for just even a brief second. Okay? Now, if you take a look at, for instance, if you let air out of a hose, out of a air compressor, man, it gets cold. Well, why is that? Well, because you're reducing the pressure on it, and when you reduce the pressure, the volume is can't stay on both sides. As the pressure goes down, what else? The temperature has to go down. They have to go the same direction. Okay. And another thing you can think of is when you have a balloon and you step down on it, what are you doing? You're increasing the pressure, so the pressure will go up. Okay, but if the temperature stays the same, if the pressure goes up, that's because the volume went down, right? When you stepped on it, you squished it. Okay, so that stuff's all pretty straightforward. We can do that till we're blue in the face, and we will. Okay, but the ideal gas law is a big deal. Now, if you're in Ford's class, technically it's PV over T. No, PV equals nRT. Equals nRT. And if that's technically what it actually is, in a chemistry class, that matters. Because in a chemistry class, we get all excited about how many molecules there are and all that garbage, right? We don't get that excited about that in physics. We just go, hey, PV over T, well, PV over T rather, is equal to nR, but those are constants. And so we don't really care what that constant is. We just say, hey, it won't change. So PV1 is equal to P2 V2 over T2. It's just a constant. Okay? And that's the way that we're going to handle it in our class. Okay? All right. So the kind of problems that you'll see on the homework for 13.1 that we're going to focus on are things like this. Okay? Yeah. So in the old, by the way, in the old days, we used to leave a lot of gaps in our train, in our railroads, or bridges. Bridges we still do. We don't really do it with trains anymore because they found out there's other ways of handling that. But yeah, so let's say you want to have a gap so that when they just barely touch. So these rails are 10 meters long. Okay. And currently they are at 10 degrees C. Oh, I'm sorry, they're 20 degrees C, and they just barely touch. They barely touch at 30 degrees C. Okay, well, they're steel rails, so delta length equals, okay, and so the idea is they each are going to be growing half as much. I mean, they grow half as much of it. Okay, so whatever we get for the distance for one, we're going to put on the other one too, right? That makes sense. So the delta length here goes like this. It is alpha length naught delta t, and so 1.2 e minus 5. The original length is 10, and the change in t is also 10. So 1.2 so that's a millimeter. So about 2.5 millimeters apart, because you double that because each one are going to grow. If you do that, you're good to go. Now, 2.5 millimeters is diddly squat, so you don't have to worry about it too much, from a change of temperature of 10 degrees. What they figure is now, for most of the time, when they lay a railroad out, they lay a railroad in weather such that it is the predominant temperature of the year will be at that temperature. And so then what they'll notice is it really doesn't expand enough to worry about. Now, there were some times in the old days when they put them side by side together and it gets super hot, and it's not really a big deal anymore. In fact, they do a lot of welding of railroad tracks now, so it doesn't really make as big a difference as it used to be. Okay? We used to think it was a bigger deal. It's really not that big a deal anymore. I found out from the railroads. Okay. A train begins a journey at 100 kilometers an hour. It's got steel wheels, obviously, yes. And the wheels heat up while the engine keeps a constant RPM. What rise in temperature do they need to get to 100 kilometers per hour? Okay. So here's the thing. It doesn't really make any difference in terms of that. When you think about it, I need to go from 100 to 101 100.1 kilometers per hour. Okay, we got a diameter here, right? Okay, so we've got some RPM. Okay, I don't know what it is right now. We'll worry about that in a second. And so it doesn't matter because percentage-wise, it will be the same. If we have a 1 meter wheel, then it's going to be turning a certain number of RPMs to pull this off. Okay. If it's a 2 meter wheel, it's going to be turning half as fast to still pull it off. Okay. But regardless, we'll still get the same temperature swing either way. So if you think about that, let's go with that. So I'm going to say that my wheel is 1 meter in diameter, because I think that will make it easier for me to understand initially. So 100 kilometers an hour, we need that in meters per second, I think is what we really need. So let's do it on the thing over here. 100 kilometers an hour. Not miles per hour, you dumbass. Meters per second. 27.777777. Sweet. 27.777 meters per second. All right, cool. So what kind of RPM would you need to pull that off? Well, what do I mean? Well, every time it goes around, that's 6.24. 6.24. That's meters per revolution. Right? Because it's 2 pi. And I did it that way on purpose. So pi times, actually it's pi times the diameter. Sorry. Circumference is pi times the diameter. So 3.14 meters per revolution. Okay. And so if I do that, 27.777 divided by pi, and I get about 8.8 revolutions it takes. Takes about 8.8 revolutions to go 27.7 meters in a second. Do I believe that? I do. That means it takes, right, so that's revolutions, 8.8 revolutions. That's what it's going to take. Okay, what does that mean? It means it's 8.8 revolutions per second. Right? 8.8 revolutions per second. Times 60. I think he's going to have to be doing about 530 RPM. Okay? Now, I just do that just because, hey, whatever. That's what I need to have. Now, what I should have done is I probably shouldn't have rounded as hard as I did because of the fact that when I do 100.1, it's not going to change much, right? So I probably should have done in my calculator 27.77777. Divide by pi. So 8.8 times 60 is 530.51. Okay, nice. Now, that part isn't going to change. Okay. So then the question is simply this is to get to 100.1, we got to look at what our diameter needs to increase to. So if I do this, well, in here rather. No, in here. 100.1 27.8055 27.8055. Nice. Now, I need to have still being 8.8 revolutions. Yes? That makes sense? So, divided by, so 27.8055, 27.805555 divided by pi. As you can see, I need to have 8.85. Oh, you stupid idiot. Just a minute. Try it again, Jay. 27.8. 27 divided by 8.84. I need the same revolutions. Are you with me? So I need to have a circumference that, I need to have a circumference of that. Now, if I divide that by pi, I get 1.001. So I need to increase it by 0.001 for my delta length. E minus 5. My original length, 1. Now you're going to notice that doesn't make any difference in a second. Times my delta t. And so if I do that, 0.001 divided by 1.2 minus 5. It would need to increase in temperature by 83 degrees. Okay. Now what I mean by that is this. It doesn't make any difference, right? Let's say I had a smaller one. Suppose this was 0.5 instead of 1. This would be what? Your speed, 27.7 meters per second, would be the same, but this would be doubled because the wheel is half as big, right? That part didn't change. This circumference would have gotten half as big. That's true. That's true. But it would have done the same. It proportionally would have been exactly the same deal. Okay? And so that's one of those problems where in our physics book, which I really like it, is it throws a lot of problems out there where it seems like it doesn't matter. At first you're like, well, does it matter? Well, I don't know. Try it. And in most cases, it doesn't actually matter because like things like the original will just cancel out and go away anyways. Yeah, so it's pretty nice. A 1 liter Pyrex beaker is filled to the brim at 20 degrees C. So here's your beaker. There's water in it. 20 degrees C. It's a Pyrex container. And when it's heated to, the whole kit and caboodle is heated to, oh no. When it's heated, 15 cc's. Is that what I said? Yes. Of water overflow. What is new temp? Okay. Well, guess what happens? Pyrex doesn't expand as much as water. That's the whole reason we use Pyrex. So Pyrex is great because you can get it hot, you can get it cold, and it does not change volumes, okay? If you made a measuring cup out of something that when you put hot water in or hot something in got changed, got bigger, then you would weigh, it would measure less stuff because it would expand. It's not really optimal. And so it's also good for pulling out of the fridge and putting it in the freezer and so forth, and putting it in the oven. Except for a couple years ago, I'll never forget, I made this new recipe. You cook these potatoes in the stove in the oven in these Pyrex pans. You take them out, you let them cool down for a while, and they were so cool that I could touch the pans with my bare hands, and it wasn't even hot. So then I took and I poured boiling chicken broth into them, and both pans shattered to bits. And I'm like, what? Huh? Mind-boggling. That should not have happened. Scared the crap out of me. And of course, I was in the kitchen in my bare feet. So hot water and shards of glass. Woohoo! That was fun, this room. But what we're going to be looking at here is, again, thermal expansion. And so for water, it is 2.1 E minus 4. Water, 2.1 E minus 4. And for Pyrex, it's significantly less than that. That's, again, the whole point, is 0.09 E minus 4. Okay? So here's what I know. That the water, okay, oh, here's what I know. I know that I had water. So I had the delta volume of the water was beta volume naught delta T. And I know that delta volume for the Pyrex was beta V naught delta T. And what do I know? Well, I know that the volumes, I know that when I subtract them, I know that this volume minus this volume is, what did I say? 15 cc's. Now let's recall 1 liter is equal to 1,000 cc's. So I think what I'm going to do is, well, so what I know is this. I know that this is for water. This is Pyrex. I know that if I take beta for water times volume for water, delta T for water minus beta for Pyrex, V naught for Pyrex, delta T for Pyrex better equal 0.01. Better equal 15. Okay, that's what I know. Okay, well, here's also what I know. These guys have a delta T in common, so you could factor it out. So that's 2.1 E minus 4 times 1,000 minus 0.09 E minus 4 times 1,000 equals 15. So if you were to simply open up a calculator, it would be helpful. There you go. Thank you. Take 15, divide by 2.1 E minus 4 times 1,000 minus 0.09 E minus 4 times 1,000. And you find it needs to be about 75 degrees C change in temperature. Okay? That is how much it would come out. Okay, and so did it say what the initial temperature was? I think it did. I think it said it was 20. Let's see if that's true. Yes, it's 20. So it was at 20 degrees C initially. So we need to get it to 95 degrees C for that to happen. So just under boiling. Yay! Here's one. How much air? Oh no. The containers. Okay, so let's see. All right, so it says a piston is holding air trapped in here of some kind or another. Doesn't say. A piston maintains a constant percent pressure on a sample of helium. Excellent. Helium. When the temperature is 27 degrees, the volume is 1 liter. When heated the volume is 1.2 liters. What is the new temp? Okay. Well, what did it say? It said the pressure is constant. So that's Charles' law. But if you're not sure, hey, can I just do ideal gas law? That's what I heard. Pressure's constant. Boom, there we go. Are you with me? It's that easy, friends. 1 1.2. I want to put 27. Don't do it! What do you mean, groom? I need Kelvin, baby. So 27 plus 273 is 3 honey. And then temperature new over here. So 3 honey times 1.2 is 360. The new temperature is 360 degrees K. And if you want that back to Celsius, it's 87 degrees C. And that's pretty darn hot if you want it in Fahrenheit. All right, but whatever. It's still toasty. But it'll burn you, Mr. Groom. Sure. Okay, so I don't know. That's probably enough problems for you today. That's kind of where we're going with 13. We'll do some more examples. Going to be another video later this week. Hope that helps.